Go outside tonight, far enough from any town that the sky comes back, and let your eyes adjust. A band of pale light appears overhead, running from one horizon to the other. That band is not something in the sky. It is a wall of 100 billion suns, and you are standing inside it. A particle of light that left its far edge when our species first existed is only a third of the way here. Our fastest machine, flying without stopping for 49 years, has crossed a rounding error of it. Its centre sits 26,000 light-years away, in a direction you can point to with your finger, and no human eye has ever received a single photon from it. There is one question about that band, and it sounds like arithmetic. How long would it take to cross it? By the end of tonight you will have 3 separate answers, all of them correct, and the last one will not be a number at all. Get comfortable. If you are the kind of person who enjoys having a familiar sight quietly taken apart, a quick like and subscribe helps this channel reach more curious minds like you. Because by the end of this, the word across is going to stop meaning what you think it means. Now, let's gently drift into this. Somewhere far from any town, on a night with no moon and no cloud, a band of pale light arches across the sky from one horizon to the other. It is not bright. It does not announce itself. Most people alive today have never seen it, because the glow of the places we live has washed it out of the sky entirely. But if you drive far enough, and wait long enough for your eyes to adjust, it appears a soft, uneven river of light, brighter in some stretches, torn by dark rifts in others, running right across the middle of everything. Ancient people saw a road, or a river, or spilled milk. That last one stuck, and it is why we call the thing we live inside the Milky Way. Here is the first thing worth understanding about that band, and it is a strange one. It is not an object in the sky. It is not a cloud, or a structure, or a feature sitting out there among the stars. It is the sky. It is what you see when you look in one particular direction, the direction in which the stars in front of you are stacked deepest. Think of yourself standing in the middle of a very large, very flat room. If you look up at the ceiling, or down at the floor, you're looking through the shortest possible distance, and you can see straight out of the room. But if you look sideways, along the length of the room, you're looking through the longest possible stretch of it, and everything in that direction piles up in your line of sight until it merges into a single unbroken glow. That is the band. You're not looking at a wall. You're looking at a wall edge-on from inside it. And when you turn 90 degrees and look at the empty dark parts of the sky, you're not looking at less galaxy. You're looking out of it, through the thin dimension, into the space beyond. There are details in that band which give the game away, once you know to look for them. It is not uniform. One stretch of it, low in the southern sky in the summer months, is noticeably richer and brighter than the rest, and that stretch lies in the direction of the constellation Sagittarius. That is not a coincidence of arrangement. That is the direction of the centre, and the band is brighter there because there is simply more galaxy in that line of sight than in any other. Look the opposite way, toward Auriga in the winter sky, and the band thins and fades, because in that direction you are looking outward toward the rim and running out of galaxy sooner. Then there are the dark rifts, the ragged black channels that split the band lengthwise and look, to the eye, like gaps. They are not gaps. There is no missing region of stars there. Those are clouds of interstellar dust sitting between us and the light, blocking it. The band has holes in it, for the same reason a window has a shadow across it, and those dust clouds are going to become one of the most important characters in this entire story. Every human being who has ever lived has looked at that band and never once seen the thing they were actually looking at. Because the band, as your eye receives it, is a lie of scale. It looks like a feature. It is a cross-section. Now stay with me for a moment, because there is a second thing hiding in that night sky that is even harder to accept. Look at the stars, not the band, the individual points of light scattered across the rest of the sky. Pick out the brightest one you can find. Trace a constellation you recognize. Those stars feel like the far edge of things. They feel like distance itself, like the outer boundary of what exists. They are the furthest away anything has ever felt. They are not far away at all. They are essentially next door. Across the entire celestial sphere, the unaided human eye can register somewhere around 9,000 stars, and from any one spot on the ground on any one night, you might see 2,000 to 3,000 of them at best. and almost every single one of them lies within about 1,000 to 4,000 light-years of where you're standing. A small handful of monsters push further. Deneb, in the Tale of Cygnus, is around 2,600 light-years out, and blazing so violently it stays visible anyway. There are a couple of even more extreme outliers hiding in the star catalogues. But the working bubble of naked-eye vision is a sphere a few thousand light-years wide. That is the whole of it. That is the entire visible universe as far as the human eye alone is concerned. Every star you have ever pointed at, every constellation anyone has ever named, every point of light in every night sky in all of human history, all of it sits inside a bubble a few thousand light-years across. And the disk of stars you're standing in, the wall you have been looking at edge on your entire life, is 100,000 light-years wide. Take a second with that ratio, because the numbers are so lopsided they slide off the mind. If the galaxy's disk were the length of a football pitch, everything you have ever seen with your own eyes would be a coin lying somewhere near the centre circle. If the galaxy were the width of a city, your entire personal night sky would be one room in one building. The stars are not the far edge of anything. They are the nearest possible neighbours, and beyond them, in every direction along that flat plane, the galaxy keeps going for tens of thousands of light-years past anything a human eye can resolve. So the band of milky light is not made of stars you can see. It is made of stars you cannot. It is the combined, blurred, unresolvable glow of hundreds of millions of suns too distant and too faint to separate into points. Your eye simply gives up trying and hands you an average. For most of human history, nobody knew that. The band was a substance, not a population. Something spilled, something poured. Then, in 1610, a man in Padua pointed a tube with 2 pieces of ground glass in it at that band, and it fell apart. Galileo looked at the Milky Way through a telescope with less light-gathering power than a modern pair of binoculars, and the smooth river of light broke into individual points, and kept breaking, further than his instrument could follow. That is the moment the question in this video becomes possible to ask, because as soon as the band is made of stars, it has a shape, and if it has a shape, it has a size, and if it has a size, then there is a number, a real, specific, physical number, for how far it is from one side of it to the other, and there is a follow-up question, which is the one this whole thing is really about, and which I want to put in front of you right now so that it sits with you for the next 2 hours. How long would it take to cross it? Not how far, how long? Because the distance turns out to be the easy half of the problem, and the time turns out to be where everything gets strange. I am going to answer that question tonight. I am going to answer it properly, with real numbers from real physics. But I am going to answer it 3 separate times, and the first 2 answers are going to feel complete, and they are both going to turn out to be answers to a slightly different question than the one I just asked. The third answer is the one that does the damage. It arrives near the end, and when it arrives, it does not just give you a number. It takes the question apart and shows you that it was never quite the question you thought it was. Before any of that, though, we have to establish what we are crossing, and that is harder than it sounds, because we are trying to measure a room from inside it, with no way to step outside and look, and with a great deal of the room hidden behind dust. Consider what that actually demands. If you want to know the size and shape of a building, you walk out of the front door and look at it. Nobody has ever done that with the Milky Way. No spacecraft has ever travelled far enough to turn around and photograph our galaxy from outside, and I will show you the arithmetic on this later, and it is brutal. No spacecraft ever will. Not with any propulsion humans have built, not with any propulsion currently on a drawing board, which means something worth saying plainly right at the start. Every image you have ever seen of the Milky Way, the beautiful face on spiral with the glowing core, and the elegant sweeping arms and the little arrow pointing to a spot near the edge saying "you are here," is a drawing. Every single one. It is either an artist's impression, or it is a computer reconstruction assembled from measurements taken from our one fixed seat inside the thing. Some of those reconstructions are extremely good. None of them is a photograph, because a photograph is not possible. We know more about the individual stars of this galaxy than about any other galaxy in the universe. We have catalogued nearly 2 billion of them individually, with positions and motions and distances, and we cannot take its picture. It is the one galaxy in all of existence that we are structurally unable to see. So how does anyone know it is 100,000 light-years across? How does anyone know its shape, or where we sit in it, or what lies at the middle? Where does a number like that even come from, if nobody has ever stood far enough away to check? The answer to that involves a comet hunter who counted stars until his eyes gave out, a man who was completely wrong for entirely reasonable reasons, and a discovery that quietly removed us from the centre of the universe for the second time in 300 years, and it starts with dust. Between the stars there is soot, not much of it by any ordinary standard. If you took a cubic kilometre of interstellar space and swept up every grain of dust in it, you would struggle to fill a thimble. The grains themselves are tiny, carbon and silicate particles, most of them smaller than the wavelength of the light they interfere with, thrown off by dying stars and drifting in the space between. It is the thinnest smoke imaginable, but there is 100,000 light-years of it, and thin smoke stacked deep enough is a wall. This is the single most important obstacle in the history of trying to measure our own galaxy, and it is worth understanding exactly how it deceives. Dust does two things to starlight. It dims it and it reddens it, scattering blue light more effectively than red, which is why distant stars in the plane of the galaxy look both fainter and warmer in colour than they actually are. And for most of the history of astronomy, nobody knew it was there, which means that for 2 centuries, every attempt to measure the size of the Milky Way was made by people looking through a fog they could not detect, and interpreting the fading of distant stars as distance rather than as absorption. The stars got dimmer with distance, exactly as they should. They just got dimmer faster than they should have, and nobody knew. The first serious attempt came from a musician, William Herschel, who discovered Uranus and built the finest telescopes of his era in his own workshop, decided in the 1780s to simply count. He divided the sky into hundreds of sample regions and counted the stars he could see in each one, on the reasonable assumption that if he could see further in a given direction, there would be more stars piled up in it. He called them star gauges, and his sister Caroline recorded the numbers while he worked through the nights. What he produced was the first map of the Milky Way ever made, a lumpy, irregular slab of stars wider than it was thick, with the sun sitting more or less in the middle of it. As a piece of observational work it was magnificent. As a map it was wrong in 2 crucial ways, and both errors came from the soot. Because dust cut off his view at roughly the same distance in every direction along the plane, the galaxy appeared to have a boundary, and because that artificial boundary was roughly equidistant from him in all directions, he appeared to be standing at the centre of it. Herschel had, in effect, measured the size of the dust and mistaken it for the size of the galaxy. That error persisted in more sophisticated forms for well over a century. As late as 1922, the Dutch astronomer Jacobus Kapteyn published a careful statistical model of the stellar system, enormously more rigorous than Herschel's, built on proper motions and parallaxes and star counts, which concluded that the Milky Way was a flattened system roughly 40,000 light-years across, with the Sun near, though not exactly at, its centre. Kapteyn was one of the finest observational astronomers of his generation. He had the wrong answer by a factor of several, and he had it for the same reason Herschel did. So how did anyone ever get past it? And keep the crossing question in mind while I answer that, because everything I am about to describe is the machinery that produced the number we are eventually going to try to cross. The way past the dust was to stop looking through it. In 1918, an American astronomer named Harlow Shapley did something that seems obvious in hindsight and was not obvious at all at the time. Instead of studying stars in the plane of the Milky Way, where the dust is thickest, he studied globular clusters, dense, roughly spherical swarms of hundreds of thousands of very old stars, which are distributed not in the disk but all around it, above and below the plane where the view is comparatively clear. He measured distances to those clusters using variable stars inside them, and then he plotted where they were, and the pattern that came out was not centred on the Sun. It was not centred anywhere near the Sun. The globular clusters were clustered overwhelmingly around a point tens of thousands of light-years away in the direction of Sagittarius. That is the direction where the band of light is brightest. Shapley had found the centre of the galaxy, and it was not here. It was the second time in 300 years that a careful measurement had moved humanity out of the middle of things. Copernicus took the Earth out of the centre of the solar system. Shapley took the solar system out of the centre of the galaxy, and the reaction was, predictably, resistance. His figure was too large for many of his colleagues to accept, and in fact he had overestimated the galaxy's size by roughly a factor of 3, because he had not corrected for the dust either. But the shape of his answer was right, and the position was right, and after that nobody could put us back in the middle. 2 years later, in 1920, Shapley stood up in a hall at the Smithsonian in Washington to argue the point in public against an astronomer named Heber Curtis in a session that has been known ever since as the Great Debate. The question on the table was not only how big the Milky Way was, but whether the faint spiral smudges catalogued across the sky were structures inside it or separate systems entirely. Shapley said the galaxy was enormous and the spirals were part of it. Curtis said the galaxy was smaller and the spirals were other galaxies, unimaginably far away. They were each half right and each half wrong, which is roughly the best outcome any scientific debate ever achieves. Shapley had the scale of the galaxy closer to correct. Curtis had the spirals correct. 4 years later, Edwin Hubble found variable stars in the Andromeda spiral, measured their distance and settled it. Andromeda was outside. The Milky Way was not the universe. It was one object in it, and now it needed measuring as an object. Now think about what has happened by this point in the story. We have established there is a centre, and that we are not at it. We have not established how wide the whole structure is, and every method used so far has been systematically defeated by a substance nobody could see. What was needed was a way to see through the dust rather than around it, and that took another few decades and a complete change of instrument. The breakthrough came from a prediction made during the Second World War. A Dutch student named Hendrik van der Hulst, working under occupation, calculated in 1944 that neutral hydrogen atoms, by far the most abundant material in the galaxy, should very occasionally emit radio waves at a wavelength of 21 centimeters. It is an extraordinarily rare event for any individual atom, but there is an extraordinary quantity of hydrogen, and the signal should be detectable. In 1951 it was detected, and it changed everything, because radio waves at 21 centimeters do not care about dust at all. They pass straight through it as if it were not there. For the first time, astronomers could map the distribution of material right across the galaxy, through the plane, past the centre, out to the far side. Combine those maps with the Doppler shift of the signal, which tells you how fast each cloud of hydrogen is moving toward or away from you, and a rotating structure begins to assemble itself out of the data. The dust had been beaten, not removed but rendered irrelevant by simply choosing a wavelength it could not touch. Everything since has been refinement, and the refinements have been ferocious. Radio interferometers, linking telescopes across continents to act as a single instrument thousands of kilometers wide, have measured the positions of masers, natural microwave beacons in massive star-forming regions, precisely enough to fix their distances by pure geometry, pinning down the location of spiral arms directly rather than inferring them. Infrared surveys, which also see through dust, revealed in the 1990s and 2000s that our galaxy is not a simple spiral at all, but a barred one, with a straight elongated structure running through its middle that nobody had confirmed before. And then there is the survey that changed the scale of the whole enterprise. The Gaia spacecraft, launched by the European Space Agency, has spent over a decade measuring the positions, distances and motions of individual stars with a precision measured in tens of microarc seconds, an angular precision equivalent to picking out the width of a human hair from more than 1,000 kilometers away. Gaia has catalogued nearly 2 billion stars. That number deserves a moment, because it cuts both ways. 2 billion individual stars, each with a measured position and a measured motion, is the largest map of anything humans have ever made, and it is roughly 1% of the galaxy. 1%. After the finest astrometric instrument ever flown has spent more than 10 years doing nothing else, we have individually catalogued about 1 star in 100. The other 99% remain a statistical population, real, accounted for in the models, and never individually seen. So this is the honest position we're in as we approach the actual dimensions. Nobody has ever photographed this galaxy. The view in visible light is blocked in the most important directions. The numbers we have were assembled by counting, by triangulating, by listening at wavelengths the eye cannot register, and by inference from a single fixed vantage point that has not moved in any meaningful way for the entire history of the science. And yet the numbers are good. This is the part that ought to impress rather than unsettle. The distance to the centre of our galaxy is now known to a precision of better than 1 part in 600, and I will show you exactly how in a while, because the method is one of the most elegant things in modern astronomy. The map was drawn by people who knew, every one of them, that they would never see the thing they were drawing. Which brings us to what they drew, because when you assemble all of it, the star counts and the globular clusters and the hydrogen maps and the masses and the 2 billion Gaia stars, a shape emerges, and the shape is not the one in the illustrations. It is flatter than you think, and stranger than you think, and it is bent. Find a compact disc or a DVD and hold it flat on your palm. It is 12 centimeters across. It is 1.2 millimeters thick. That is a ratio of exactly 100 to 1, width to depth, and it is the closest everyday object we have to the true proportions of the star-forming disk of our galaxy. 100,000 light-years across, about 1,000 light-years thick. That thin disk, the layer where essentially all the young stars live, where the gas is, where the dust is, where every nebula you have ever seen a photograph of sits, would fit inside the plastic of the disk in your hand, not spread across its face, inside its thickness. Everything bright and everything new in this galaxy is confined to a sheet whose depth is 1% of its width. Almost no illustration shows you this. Every picture of a galaxy seen edge-on exaggerates the vertical dimension, because if you drew it honestly at any size that fits on a page, the disk would be a line. It would have no visible thickness at all, and so the mental image most people carry, a sort of lens or a fat discus, thick in the middle and tapering out, is significantly wrong in the direction that matters most. We are not living in a lens, we are living in a sheet. If you want the comparison to bite even harder, take a single sheet of ordinary printer paper. It is about 210 millimeters wide and about 1/10 of a millimeter thick, a ratio of roughly 2,100 to 1. So the galaxy is not quite as flat as paper, it is about 20 times thicker, proportionally. That is the entire correction. When somebody tells you the Milky Way is thin, the honest translation is that it sits somewhere between a compact disc and a sheet of paper, and it is very much closer to the paper end than to anything you would call an object with depth. And the flatness is not decoration. It is a direct consequence of how the thing formed. A cloud of gas collapsing under its own gravity while rotating cannot collapse evenly. It falls freely along its spin axis because nothing opposes gravity in that direction, and it resists collapsing inward across the equator because the rotation holds it out. So it flattens. Every disk in the universe, the rings of Saturn, the plane of our solar system, the disk of this galaxy, is the same piece of physics running at a different size. Flatness is what rotation does to anything that falls. Now, that sheet is the bright part, and this is where the honest complications begin, because the galaxy has layers, and each one is a different kind of object. The thin disk is the young one. Its stars have relatively high abundances of heavy elements, carbon, oxygen, iron, everything forged inside earlier generations of stars and returned to space when they died. They orbit in near-circular paths, all going the same way, all staying close to the plane. The Sun is one of them. This is the galaxy's active layer, and it is where anything is still being built. Wrapped around it and passing through it is the thick disk, extending something like 3,000 to 4,000 light-years vertically. Its stars are older, poorer in heavy elements, and moving on more tilted, more disordered orbits. The thick disk is generally read as a fossil, either stars born in the original disk and then shaken upward by ancient collisions, or stars stolen wholesale from smaller galaxies that our galaxy swallowed billions of years ago. When you look at the thick disk, you are looking at damage. It is the record of a violent childhood, still legible in the way those stars move. Around all of it is the stellar halo, a roughly spherical, extremely sparse distribution of the oldest stars in the galaxy, along with about 150 globular clusters, the same objects Shapley used to find the centre. Halo stars are ancient, metal-poor and on wildly inclined orbits that plunge in toward the centre and back out again. Some of them are nearly as old as the universe, and at the middle sits the bulge, roughly 10,000 light-years across, packed with old stars and running straight through it, a bar. That bar is worth pausing on because its discovery is a good demonstration of how recently we learned what we live in. A bar is a straight, elongated concentration of stars through the centre of a galaxy, out of which the spiral arms trail. We can see them easily in other galaxies. In our own, the bar is buried behind the thickest dust in the sky, viewed almost end-on from our position, and its existence was suspected for decades but not properly confirmed until infrared surveys mapped the inner galaxy in the 1990s and 2000s. It is roughly 27,000 light-years long, tilted at an angle to our line of sight, and it was hiding in plain view the entire time. We have been living in a barred spiral galaxy for the whole of human existence, and only found out about it in living memory. Keep the crossing question with you here, because the shape matters enormously to it. If you wanted to travel from one side of the galaxy to the other, the flatness is the single most useful fact available to you. You would not go through the middle. The middle is crowded and violent and gravitationally hostile. You would climb slightly out of the plane, cross above the disk through nearly empty halo space, and drop back in on the far side. The disk being 1% as thick as it is wide means that stepping out of it is cheap, and staying out of it costs you nothing. The obstacle is never the material, it is only ever the distance. But now I have to complicate the shape because the disk is not a clean flat sheet, it is bent. Astronomers first found this in the 1950s in radio maps of neutral hydrogen. The outer parts of the disk do not lie in the same plane as the inner parts. On one side, the disk curves upward. On the opposite side, it curves down. Seen edge-on, our galaxy has a gentle S shape, like a vinyl record left too long in a warm car. The warp is small in relative terms and enormous in absolute terms. Thousands of light-years of vertical displacement at the outer radii. Gaia mapped that warp in detail and found something stranger still. The warp appears to move. The direction of the bend precesses around the galaxy, like the wobble of a spinning coin as it settles. And here the story gets genuinely unresolved, because different research groups measuring different tracer populations get different answers for how fast that precession happens. Early Gaia analyses reported a comparatively rapid rate. More recent work using classical Cepheid variables as tracers reports something closer to 5 km per second per kiloparsec. Other analyses of the outer disk report a similar low value, with systematic uncertainties comparable in size to the measurement itself. That is a disagreement of roughly a factor of 2 on a basic structural property of the galaxy we live in, published openly in the literature, still being argued about right now. Nor is there agreement on what is doing the bending. Some models point at the Large Magellanic Cloud, a substantial satellite galaxy currently swinging past us. Some point at the Sagittarius dwarf galaxy, which is being torn apart by our gravity as we watch. A modelling study published in 2026 argues that the ancient collision with a galaxy called Gaia Sausage Enceladus, 8 to 11 billion years ago, can reproduce the warp we observe if the Milky Way's total mass is toward the lower end of the plausible range. Something bent our galaxy. We do not know what, and there is one more distortion, which is going to matter a great deal in a while. The disk flares, its vertical thickness increases with distance from the centre, so the outer regions are proportionally puffier and more diffuse than the inner ones. The sheet gets thicker and fainter as it goes out, and it does not stop at any particular radius. It thins out. Hold on to that, because it is the seed of a problem I'm going to bring back later. A structure that fades rather than ends does not have an edge. It has a threshold, and somebody has to choose where to put it. So we have a warped, flaring, layered sheet with a bar through its middle. What about the arms? This is where our position inside the galaxy causes the most trouble, and where the honest answer is the least satisfying. We do not confidently know how many spiral arms our galaxy has. For most of the 20th century, the working picture was 4 major arms, named, in the way astronomers name things, after the constellations in which we see them: Perseus, Sagittarius Carina, Scutum Centaurus, and Norma. Then infrared star counts from the Spitzer Space Telescope, which traced the bulk of the stellar mass rather than the bright young stars, suggested that in stars the galaxy really has only 2 dominant arms. Meanwhile, radio observations of mesas in massive star-forming regions kept supporting 4 arms in the gas. The current reconciliation is a hybrid, a 2-armed pattern dominating the interstellar distribution, with 4 arms traced in gas and young stars further out, branching from the inner structure. And even that is shifting. Recent mapping work that incorporates X-ray observations from Chandra and from the XMM Newton Observatory places the 2 outermost arms further from the centre than earlier maps had them. The reason none of this settles is straightforward. Determining the spiral structure of a galaxy from a seat inside its disk, at one fixed radius, looking through dust, is close to the hardest possible version of the problem. If you were floating a few million light-years above the plane, you would resolve the entire argument in a single photograph. Nobody has ever been there, and one detail about arms which quietly deflates a common misconception. Spiral arms are not solid structures made of fixed stars. They cannot be, because the galaxy rotates differentially. Material closer in completes an orbit much faster than material further out, so any fixed pattern of stars would wind itself into a tight coil within a couple of rotations and disappear. Arms are understood instead as density waves, regions where the orbits of stars and gas bunch up temporarily as they pass through, like a traffic jam that persists in place while individual cars flow in and out of it. Which means the arms are not places, they are congestion, and the enhancement is modest. An arm might be 10 or 20% denser than its surroundings. Crossing one would not be an event. You would not see a wall of stars. You would pass through a region with slightly more traffic, over a span of tens of millions of years, and never notice. So this is the object. A sheet 100,000 light-years wide and 1,000 thick, bent by something unidentified, thickening toward its rim, wrapped in an older, thicker layer and a sparse ancient halo, with a bar through its center and an unresolved number of density waves winding out of it. That is the shape. Now we need the contents, and this is the part that reverses everything, because when you actually go and look at what is inside that sheet, you find that the defining feature of a galaxy is not its stars. It is how astonishingly little of it there is. Pick up a single grain of sand and hold it between your finger and your thumb. That grain is about 1 millimeter across. Let it be the sun. At that scale, everything familiar shrinks to almost nothing. The Earth is an invisible speck of dust 9 centimeters away from the grain. You could not see it if it were there. Jupiter is a barely visible mote about 0.5 meter out. The orbit of Neptune, the outermost planet, is a circle roughly 6.5 meters across, drawn around the grain in your fingers. That circle contains every world anyone has ever photographed, every place any human machine has ever landed, the entire theatre of the space age. 6.5 meters. Now walk. Walk away from the grain in a straight line. After 10 meters, the solar system is behind you. After 100, there is nothing. After 1 kilometer, still nothing. No dust, no light, no object of any kind. Only vacuum in every direction. Keep walking. 5 kilometers. 10. 20. Nothing has happened. Nothing at all has happened for the entire distance. At 29 kilometers, you find a second grain of sand. That is Proxima Centauri. That is the nearest star to our own, 4.24 light-years away, the closest neighbour we have in the entire universe. 2 specks of sand 29 kilometers apart, with absolutely nothing between them. Now hold that model steady, and let the rest of the galaxy assemble around you at the same scale. Grains of sand scattered on average tens of kilometers apart, filling a disk that is, and I have done this arithmetic carefully, about 680,000 kilometers across. The distance from the Earth to the Moon is 384,000 kilometers. So at the scale where the Sun is a grain of sand, our galaxy is a sheet almost twice as wide as the gap between here and the Moon, and about 6,800 kilometers thick, which is roughly the radius of the Earth. 200 billion grains of sand in a sheet the size of the Earth's orbit around nothing, separated by tens of kilometers each. If you gathered every one of those grains together into a single pile, it would fit in a bucket. That is what a galaxy is. Not a crowd of stars. A quantity of emptiness with an almost immeasurably small amount of matter suspended in it at enormous intervals. The numbers behind the model are plain enough. In our neighbourhood, the density of stars runs to about 4/1000ths of a star per cubic light-year. 1 star for every 250 cubic light-years of space. And the space between them is not merely empty of stars, it is close to empty of everything. The average interstellar medium in the disk carries about 1 atom per cubic centimetre. In the hot, thin phase that fills the gaps between clouds, it drops to something like 1 atom per 1,000 cubic centimetres. It is worth making that first figure concrete, because a density is an abstraction, and a census is not. Within 10 light-years of the Sun, there are roughly a dozen known star systems. Within 20 light-years, somewhere around 130. That sounds like a reasonable number of neighbours until you notice the volume involved. A sphere 20 light-years in radius is around 33,000 cubic light-years of space, which is to say that our 130 neighbours are rattling around in a container so large that the distance between any two of them dwarfs everything either of them contains. And most of those neighbours are not stars you've heard of. The great majority are red dwarfs, small, cool, dim, utterly unremarkable objects, invisible to the naked eye at any of these distances. Of the roughly 130 systems within 20 light-years, only a handful contain a star you could see without a telescope. The bright familiar names in the night sky are not typical residents of this galaxy. They are the rare enormous exceptions, visible precisely because they are freakish, and their prominence in our sky has quietly biased the picture every human culture has ever formed of what is out there. For comparison, the air in the room you're in right now contains something like 25 billion molecules in every cubic centimetre, and the best vacuum ever produced in a laboratory on Earth, using pumps and cryogenics and every technique available, is still substantially denser than typical interstellar space. We cannot manufacture emptiness as good as the emptiness that fills the gaps between the stars, and there is 100,000 light-years of it out there. Now, why does this matter for the question we're chasing? Because it settles something important. The reason nothing has ever crossed this galaxy is not that the crossing is dangerous. There is nothing to hit. If you drew a straight line from one rim of the disk to the other and travelled along it, the probability of encountering anything at all, a star, a planet, a rock of any consequence, is so close to zero that it does not enter into the planning. The route is clear. The route has always been clear. The obstacle is time, and only time, and we're going to come to exactly how much of it shortly. There is a beautiful demonstration of this emptiness waiting in our future, and it involves the galaxy next door. In roughly 4 to 5 billion years, the Milky Way and the Andromeda galaxy are going to collide. Andromeda is currently 2.5 million light-years away and closing. When they meet, the two galaxies will pass through one another, and their shapes will be destroyed, and eventually they will merge into a single large elliptical system with no disk and no arms. And in the entire course of that collision, involving perhaps 1 trillion stars between them, the expected number of direct stellar impacts is essentially zero. Not low. Zero, for practical purposes. The stars are so small compared with the distances between them that two galaxies can be driven straight through each other, and the individual suns simply thread through the gaps. Orbits will be flung into new configurations. Clouds of gas will slam together, gas clouds are large enough to collide, and the merger will trigger a burst of new star formation. But the stars themselves will pass by one another like two clouds of gnats crossing a stadium. If the sun still had planets and anyone was standing on one, they would witness the sky slowly rearranging itself over hundreds of millions of years, and nothing would ever hit anything. That is how empty a galaxy is. You can run two of them into each other at full speed and nothing touches. Go back to the sand for a moment and you can see why. In the model, a star is a grain a millimetre across, and its nearest neighbour is 29 kilometres away. Now throw a second cloud of grains through the first, aimed as carefully as you like. The chance that any 1 millimetre grain finds another millimetre grain across 29 kilometres of open space is not small in the way that winning a lottery is small. It is small in a way that has no everyday comparison. You could run the collision 1,000 times and expect nothing. This is also, incidentally, one of the reasons the night sky is dark and why our galaxy has survived 13 billion years of rotation without grinding itself into anything. Systems this diffuse do not interact by contact. They interact only by gravity, at a distance, slowly, over hundreds of millions of years. A galaxy is not a machine with moving parts that touch. It is a very large number of objects falling around a common centre and almost never noticing each other at all. I should be careful here, though, because the emptiness is not uniform and the exceptions are dramatic. In the innermost few light-years of our galaxy, around the centre, the density of stars rises by a factor of something like 10 million compared with our neighbourhood. Millions of stars are packed into a volume smaller than the gap between here and Proxima. In the cores of globular clusters, those ancient swarms in the halo, stars can be separated by a fraction of a light-year, and their near encounters do genuinely happen. Close passes that strip material, that swap partners in binary systems, that occasionally produce strange rejuvenated stars called blue stragglers that look far younger than they have any right to be. So there are crowded rooms in this building. We are just not in one, and neither is most of the volume. And there is one more correction worth making because the emptiness can mislead in the opposite direction. The interstellar medium is a near-perfect vacuum at every individual point, and it is also, in total, one of the most massive components of the galaxy. Spread that one atom per cubic centimetre across 100,000 light-years of disk, and it adds up to something like 10 billion times the mass of the Sun in gas and dust. It is a vacuum that weighs 10 billion suns. Both things are true at once, and the reconciliation is simply that the volume is beyond intuition. We are at this moment sitting inside a small local example. The solar system is currently passing through a wisp of slightly denser gas called the local interstellar cloud, about 30 light-years across. That cloud sits inside a much larger cavity, the local bubble, roughly 1,000 light-years wide, blown out of the interstellar medium by a series of supernova millions of years ago. We are inside a hole in the emptiness, inside a slightly less empty patch, inside the emptiness. Which brings us back to the grain of sand, and to the thing I want to leave you with before we go further. 29 kilometres to the nearest grain. That is the smallest gap in the entire system. Every other gap is larger, and no object built by human beings has ever crossed even a meaningful fraction of that first 29 kilometres. I am going to show you exactly how far we have got in a while, and it is going to be worse than you expect. But before that, we should go and look at the one place in this galaxy where the emptiness gives out entirely. It is 26,000 light-years away. It is the reason the band of light is brightest in one direction, and no human eye has ever received a single photon from it. On a summer night in the northern hemisphere, low in the south, there is a group of stars that looks like a teapot. That is Sagittarius. And if you can find the spout of that teapot, you are pointing within a few degrees at the centre of our galaxy, the gravitational anchor around which every star you can see, including the Sun, is falling. You cannot see it. Nobody ever has. Not with the naked eye, not with the largest optical telescope ever built, not with the Hubble Space Telescope. In visible light, the centre of our own galaxy is not merely faint, it is completely, absolutely hidden, and it will stay hidden forever. The reason is the soot again, and this time the numbers are extreme. Interstellar dust lying between us and the centre absorbs and scatters visible light so effectively that the extinction along that line of sight amounts to roughly 30 magnitudes. That is an astronomer's unit, and translated into ordinary language it means the light is suppressed by a factor of about 1 trillion. 1 photon in 1 trillion gets through. Put practically, in visible light, looking along the plane of the galaxy, we can see about 6,000 light-years before the view simply closes. 6,000 out of 26,000 to the centre. We cannot see even a quarter of the way to the middle of our own galaxy, using the kind of light our eyes evolved to detect. For the whole of human history, right up until the 1930s, that was the end of the matter. The centre was a direction, not a place. Then a young engineer working for Bell Telephone Laboratories in New Jersey was given a mildly irritating assignment. Karl Jansky was asked to find out what was causing static on transatlantic radio telephone calls. He built a rotating antenna array, a set of brass and wooden frames mounted on wheels taken from a Model T Ford, which his colleagues called the merry-go-round, and he started cataloguing sources of interference. He found thunderstorms near and far as expected, and he found a third source. A faint persistent hiss that rose and fell once a day on a cycle of 23 hours and 56 minutes. That is a very specific number. 23 hours and 56 minutes is the sidereal day, the rotation period of the Earth relative to the stars, rather than relative to the Sun. Anything that repeats on that cycle is not on the Earth and not the Sun. It is fixed to the sky. Jansky tracked it down. The hiss was coming from the direction of Sagittarius. In 1932, an engineer investigating telephone static became the first human being to detect the centre of the galaxy, at a wavelength no eye can register, and he was reassigned to other work not long afterward. Everything we know about the heart of this galaxy descends from that. Radio waves pass through the dust. Infrared largely passes through it. Visible light does not. Every image, every measurement, every number that follows was obtained at wavelengths outside human vision. And what those wavelengths found is extraordinary, and it is the reason we can now state the distance to the centre more precisely than almost any other large distance in astronomy. In the innermost region there is a swarm of stars known simply as the S-stars, orbiting something. They are not orbiting slowly. They whip around on tight elliptical paths, some of them moving at thousands of kilometres per second, a few percent of the speed of light. One of them, catalogued as S2, completes a full orbit in a little over 16 years, and at its closest approach it comes within about 17 light hours of whatever it is going around, moving at roughly 3% of light speed. 16 years is a human timescale. That is the crucial thing. It means astronomers have now watched S2 go all the way around more than once and tracked it through its most violent close pass. The instrument that did it is called gravity, and it works by combining the light of the four 8.2-meter telescopes of the Very Large Telescope in Chile so that they behave as a single instrument with the resolving power of a mirror 130 meters across. With that resolution, individual stars in the galactic center can be tracked as they move, and when you have a complete orbit of a star around a mass, Newton and Kepler hand you two things at once. You get the mass of the central object, and you get the distance to the system, because the orbit's apparent angular size and its true physical size together give you the range. It is geometry. It does not depend on any assumption about how bright anything is. The results are these. The distance from here to the centre of the Milky Way is 8,178 parsecs, plus or minus 13, which is 26,673 light-years, plus or minus 42. And the mass at the centre is 4.297 million times the mass of the Sun, with an uncertainty of about 12,000 solar masses, a precision of roughly 3 parts in 1,000, which is remarkable for anything in astrophysics. 4.3 million solar masses confined inside a region smaller than the orbit of Mercury. There is nothing in physics that can be that heavy in that little space and not be a black hole. Its event horizon is about 12.7 million kilometers across in radius, 17 times the radius of the Sun, and comfortably inside where Mercury runs. In 2022, the Event Horizon Telescope collaboration released a direct image of it, a ring of light around a dark center exactly as predicted. There is a detail in that orbit which is worth a moment, because it is one of the great quiet confirmations in modern physics. Newton's gravity predicts that a star on an elliptical orbit traces the same ellipse forever. Einstein's gravity predicts that in a strong enough field, the ellipse itself slowly rotates. The point of closest approach creeps forward a little on each lap. The effect was first noticed in the orbit of Mercury around the Sun, where it amounts to a tiny discrepancy that nobody could explain until general relativity arrived. Around a black hole 4 million times the mass of the Sun, the same effect is enormously larger, and when astronomers tracked S2 through its closest approach, they measured the shift and it matched the prediction. A theory written down in 1915, tested on a star we cannot see, orbiting an object nothing can escape, 26,000 light-years away, and it was correct to within the error bars. That is the level of confidence behind the distance figure. It is not a guess dressed up in decimals. It is a geometric measurement of an orbit, cross-checked against a 100-year-old theory that has never yet failed. Now let me take you there, because the environment around that object is unlike anywhere else in the galaxy. Imagine you're travelling inward from here, along the plane, towards Sagittarius. For the first few thousand light-years the sky ahead looks ordinary, if richer than the sky you know. Then it begins to thicken. Stars ahead of you start to dim and redden, not because they are moving away, but because you are moving into the smoke. By 6,000 light-years the view forward has closed entirely. There is no light coming from in front of you at all. You're travelling blind through a wall you cannot see, and it goes on for 20,000 light-years, and then you come out of it. The sky ahead does not brighten gradually. It floods. You emerge into the nuclear star cluster, where millions of stars are packed into a few light-years, and the sky is no longer a scattering of points on a black background. There is no black background. Stars stand shoulder to shoulder in every direction, thousands of them bright enough to cast shadows, shadows crossing shadows on any surface you set down. There is no night here. There has never been night here. A planet in this region would be lit continuously from every direction at once, with nothing you could call a sunset because there would be no single sun to set. And at the middle of that crowd, holding all of it, is something you cannot see at all. An object 4.3 million times the mass of the Sun, smaller across than the orbit of Mercury, wearing a thin ring of light bent around it by its own gravity. It is silent. It is not feeding. For its size, Sagittarius A star is one of the quietest supermassive black holes known, radiating a tiny fraction of what it could. 4 million suns of mass, and it barely makes a sound. There is something worth sitting with in that quietness. We tend to imagine the centre of a galaxy as the most violent place available, a maelstrom, a furnace, something actively tearing matter apart. In some galaxies that is exactly right. The brightest objects in the universe are supermassive black holes in the middle of feeding. Ours is not doing that. Ours has, for the most part, finished eating. What is left is an object of immense mass conducting itself with almost no drama at all, occasionally catching a wisp of gas and flaring briefly at wavelengths we can watch, and otherwise simply holding 200 billion stars in place by existing. It has not always been quiet. Extending above and below the galactic plane are two enormous lobes of gamma-ray emitting gas, discovered in 2010 and known as the Fermi bubbles, each reaching something like 25,000 light-years out from the centre. They are widely read as the fossil of an outburst, evidence that a few million years ago the thing at the middle of our galaxy did something violent and we are still living inside the smoke ring. So this is the object at the centre of the room we are trying to cross. It is the most important single body in this galaxy. It is 26,673 light-years away, in a direction you can point to with your finger on any summer evening, and not one photon from it has ever entered a human eye. Which raises the obvious question about where exactly we are standing in relation to it, and the answer contains a fact about the solar system's own travels that quietly destroys the assumption underneath this entire video. The Sun is not in a spiral arm. It sits in a minor structure between two of them, a spur, a fragment, a bridge of stars and gas about 3,500 light-years wide and perhaps 20,000 long, lying between the Sagittarius arm on the inward side and the Perseus arm outward. It is called the Orion arm, or more honestly the local arm, or more honestly still the Orion spur. It is not a major feature of this galaxy, it is a side street. We sit in that side street about 26,700 light-years from the centre, which is roughly halfway out along the radius of the disk. Not central, not at the rim, halfway, in a spur, in an ordinary layer of a fairly ordinary barred spiral. That location is not a disappointment. It is a data point, and it fits a pattern that has held every single time it has been tested. The Earth is not the centre of the solar system. The Sun is not the centre of the galaxy. The galaxy is not the centre of anything. Every time we have looked for a special position, we have found an average one. Now here is what that position is doing. The Sun is falling around the galactic centre at roughly 230 kilometres every second. Some Gaia-based determinations push that a little higher, toward 235 or 240. At that speed, one complete lap of the galaxy takes about 225 to 230 million years, a period astronomers call a galactic year. The Sun has been alive for 4.6 billion years, that is roughly 20 laps. Which means the last time the solar system occupied this exact position in the galaxy, the Triassic period was beginning on Earth. The great extinction that ended the Permian had just cleared the world. The first dinosaurs were appearing. Everything that has happened since, every dinosaur, every bird, every mammal, every human being, has happened within a single lap of this galaxy. The orbit is not a clean circle in a flat plane either. The Sun bobs. It rises above the midplane of the disk, slows, falls back through, overshoots below, and comes back up again, crossing the plane roughly every 30 million years and reaching a few hundred light-years above and below at the extremes. So the true path is not a ring, but a long shallow wave wrapped around a ring, and we are currently a little above the midplane and drifting. The Sun is also almost certainly not where it was born. The chemical composition of the Sun does not quite match the composition of the material at this radius, and the mismatch points inward. The best reading is that the solar system formed considerably closer to the galactic centre and has migrated outward over billions of years, nudged by interactions with the arms and the bar. The star cluster the Sun was born into is long gone, dispersed into the general population of the disk. A handful of candidate solar siblings have been proposed from their motions, none confirmed. Every star that formed alongside ours is out there somewhere, unrecognisable, scattered around the disk. And in the course of all that travelling we have passed through spiral arms repeatedly, which sounds like it ought to have been eventful and was not. An arm is perhaps 10 or 20% denser than its surroundings, and a crossing takes tens of millions of years. There is no boundary to notice, no wall to hit, no moment of entry. You simply spend a long stretch of time in slightly heavier traffic, and then a long stretch in slightly lighter traffic, and the difference is invisible from inside. But that is not the fact I want to leave you with. This is. work out the circumference of a circle with a radius of 26,700 light-years. It comes to about 168,000 light-years. The disk of the galaxy is 100,000 light-years across, so the Sun covers more than the entire width of the galaxy on every single lap. Not once in its lifetime, every 230 million years, without pause, without effort, without any propulsion system, purely by falling. And it has done it about 20 times, which means the solar system has already travelled somewhere north of 3 million light-years, more than 30 times the full diameter of the galaxy, and it has arrived precisely nowhere. It is in the same neighbourhood, in the same spur, at the same radius, with the same view. 30 galactic diameters of distance covered, and no displacement whatsoever. That is the fact that quietly takes apart the assumption underneath this entire question. We have been treating the crossing as a problem of distance, as though the galaxy were too wide to get across, as though the number were the obstacle. It is not. The Sun eats that distance routinely. Everything in this galaxy is moving enormously fast all the time, and none of it goes anywhere, because all of it is going in circles. Distance is cheap in a galaxy. Displacement is what costs. Let me step back for a moment and restack what we have so far, because we are about halfway through, and the pieces are ready to be put together. We started with a band of light overhead, which turned out not to be an object in the sky but the sky itself, seen edge-on through a wall of stars we are standing inside. We found that every star any human eye has ever seen sits in a bubble, a few thousand light-years wide, inside a disk 100,000 light-years across. We found that nobody has ever photographed this galaxy, and nobody ever will, and that everything we know about its shape was extracted by counting stars, tracking globular clusters, and listening at wavelengths our eyes cannot register, because there is 100,000 light-years of soot between us and most of it. We found that the shape is a sheet, 100 times wider than it is thick, warped by something we have not identified, thickening toward a rim that does not have a definite location, with an unresolved number of the arms that are not solid structures but traffic jams. We found that the sheet is almost entirely empty, grains of sand 29 kilometers apart. 2 galaxies can be driven through each other without a single star touching another. We found a center we cannot see in visible light, whose distance is known to a precision of 42 light-years because we watched a star complete a 16-year orbit around it, and whose mass is 4.3 million suns held in a space smaller than Mercury's orbit. And now we have found that the solar system has already travelled 30 galactic diameters without leaving home. So the question we started with, how long would it take to cross it, is now sitting in front of us with all the necessary numbers assembled around it. The distance is 100,000 light-years. There is nothing in the way. Everything here already moves at enormous speed. It is time for the first answer, and the first answer is the fastest thing that exists. Somewhere out at the far rim of this galaxy, a star is shining, and a single particle of light has just left its surface heading in our direction. It will not arrive. Not in your lifetime, not in your species' lifetime, not in anything you would recognize as a lifetime at all. Light travels at just under 300,000 kilometers every second. It crosses the gap from the Moon to the Earth in a little over a second. It crosses from the Sun to here in about 8 minutes and 20 seconds, which means the sunlight on your skin is always a few minutes out of date. It reaches Neptune in about 4 hours. It leaves the solar system entirely in a matter of hours, and to cross this galaxy, it takes 100,000 years. That number is not really a measurement. It is the definition of the unit. A light-year is the distance light covers in a year, and the disk is 100,000 of them across, so light takes 100,000 years to get from one side to the other. It is almost circular reasoning, and that is exactly what makes it useful, because it converts a distance you cannot picture into a duration you can at least try to hold. It helps to unpack the unit itself once, because light-year gets used so casually that it stops meaning anything. 1 light-year is about 9.5 trillion kilometers. If you got in an ordinary car and drove at 100 kilometers an hour without ever stopping, no sleep, no fuel, no traffic, you would cover 1 light-year in about 11 million years, and that is 1. The galaxy is 100,000 of them wide, so try to hold it. Anatomically modern human beings, people with our skeletons, our brains, our hands, have existed for something like 300,000 years. That means a particle of light that left the far rim of this galaxy at the moment our species first appeared is, today, about 1/3 of the way across. Sit with that for a second, because it is the first genuinely difficult thing in this video. Every single thing that has ever happened to human beings has happened inside that journey. The first stone tools, the first fire kept deliberately alive, the migrations out of Africa and across every continent, the whole of the Ice Age, the first seed deliberately planted, the first wall built, the first city, the first written word, the first empire, and every empire since. Every language ever spoken and the tens of thousands that have already been forgotten. Every war, every religion, every piece of music, every person you have ever loved, and every person they ever loved. All of it fits inside 1/3 of one crossing of the room we live in by the fastest thing that exists, and nothing goes faster. This is not a limitation of our technology, and it is not a limitation of light. It is the structure of the universe. The speed of a light is not really the speed of light. It is the maximum rate at which any cause can reach any effect, and light simply happens to travel at it because it has no mass to slow it down. There is no faster. There is no shortcut at the same level of physics. 100,000 years is not the fastest crossing we know of. It is the fastest crossing that is permitted. Now let me make that concrete in the other direction, because there is a version of this you can experience personally tonight. Go outside, find Sagittarius in the south, look at the brightest part of the band, and hold your gaze on it. The light entering your eye from that direction left the region of the galactic centre about 26,600 years ago. 26,600 years ago, the Earth was in the grip of the last glacial maximum. Ice sheets kilometres thick covered most of northern Europe and much of North America. Sea levels were more than 100 metres lower than they are now, and Britain was not an island. Nobody had planted a crop. Nobody had domesticated an animal, except possibly the dog. There was no agriculture, no pottery in most of the world, no permanent settlement of any size. There were mammoths. That light set out then. It has been travelling for the entire span between the mammoths and you, at 300,000 kilometres per second, without pause, and it has only just now finished crossing a quarter of the distance to the middle of our own galaxy, and it has ended its journey by landing on your retina while you stand in a field. You cannot look at the centre of the galaxy, but you are right now looking at the Ice Age. Every time you look up, you are looking backwards. The night sky is not a picture of what is there. It is a composite photograph assembled from tens of thousands of different moments in the past, all arriving simultaneously, sorted by distance. The nearby stars are showing you the last few years. The band is showing you the last few thousand. Andromeda, if you can find it as a faint smudge in autumn, is showing you 2.5 million years ago, when our ancestors were still using the simplest stone tools. There is no way to see the galaxy as it is now. There is not even a coherent meaning to the phrase. The information cannot get here fast enough for now to be a thing you can look at. So that is the first answer to the question. How long would it take to cross the Milky Way? 100,000 years. And I want to be precise about what that answer is, because it is going to matter enormously later. That is not the crossing time. That is the crossing time as measured by anyone watching from outside, by the galaxy itself, by a clock sitting still relative to the disk, by any observer who is not the one making the trip. Nothing can beat it. If a signal left one rim of the galaxy today, no possible message, no possible objects, no possible influence of any kind could reach the far rim before 100,000 years had elapsed on the galaxy's own clock. That is a hard flaw. It is written into the geometry of space and time, and there is no way under it. Which sounds, on first hearing, like the end of the discussion. If light takes 100,000 years and nothing is faster than light, then the galaxy is uncrossable and the question is closed. Except that there is something quietly wrong with that conclusion, and it has been hiding in this section the whole time. Go back to the particle of light we started with, the one that left the far rim heading in our direction. I told you it would take 100,000 years to arrive. That is true from where we are sitting. Now ask a different question. How long does the journey take from the point of view of the particle of light itself? The answer is 0. Not a small number, not a compressed number, 0. For anything travelling at exactly the speed of light, no time passes at all. Emission and absorption are the same instant. A photon released at the far rim of the galaxy and absorbed by your eye 100,000 years later has, in its own accounting, no journey between those two events. It does not experience the crossing as fast. It does not experience the crossing. I am not going to develop that yet because it takes us straight to the end of this video, and there are several things we need to establish first. But notice what just happened. We asked how long the crossing takes. We got 100,000 years, and then we asked the same question from a different seat and got a completely different number for the same journey. Both answers are correct. Neither is an approximation of the other. Hold on to that, because it is the crack in the floor, and later on we are going to stand on it deliberately and let it give way. Also worth registering before we move on, 100,000 years feels enormous to us, and is not, on the galaxy's own terms, a long time at all. This galaxy is roughly 13.6 billion years old, nearly as old as the universe. In that span, light has had time to cross the disk about 130,000 times over. If you compressed the whole life of the Milky Way into a single calendar year, the entire recorded history of human civilization would occupy the last 0.2 of 1 second before midnight, and light would have crossed the galaxy 360 times in the meantime. Keep that thought. I am going to come back and take it apart, and the way it comes apart is one of the strangest and most beautiful results in physics. But not yet. Because before we get there, we have to be honest about our own situation, and honesty here means putting real numbers on real machines rather than on photons. Light is a useful benchmark and a terrible model. It is the one thing in the universe that is exempt from every difficulty involved in actually going somewhere. It carries no fuel because it needs none. It does not accelerate because it has always been travelling at its final speed. It does not decelerate because it cannot. It does not have to stop at the far end. It does not have to survive the journey. Nothing we can build enjoys a single one of those advantages. So the honest question is not how long light takes. Light is not going to make the trip on our behalf and report back. The honest question is how long it would take something real, something with mass, something built, something that had to be launched by an engine and had to carry its own fuel and had to arrive intact. We have built such things. 5 of them are currently leaving the solar system. One of them has been travelling for nearly 49 years and is, by an enormous margin, the most distant object human hands have ever touched. Let us see how it is getting on. On the 5th of September, 1977, a rocket lifted off from Cape Canaveral carrying a machine about the size of a small car, built around a 3.7-metre dish antenna, powered by 3 lumps of decaying plutonium. It is still going. It has never stopped. It has not been touched by a human hand in nearly 49 years, and it is currently the most distant object our species has ever made. Voyager 1 is travelling at about 17 kilometres per second relative to the Sun. That is a genuinely enormous speed by every standard we have on the ground. It is roughly 61,000 kilometres per hour. It is about 50 times faster than a rifle bullet. It would cross the Atlantic in under 6 minutes. If you fired it around the equator, it would lap the Earth in about 40 minutes. There is no human experience that prepares you for 17 kilometres per second, and no vehicle any person has ever ridden in gets within 2 orders of magnitude of it. In nearly 49 years of continuous flight at that speed, Voyager 1 has covered about 25 billion kilometres. It passed 160 times the Earth-Sun distance some time ago and keeps going. It crossed the heliopause, the boundary where the Sun's outflowing wind gives way to the material between the stars, in August of 2012. By any reasonable definition, it is in interstellar space. Convert that 25 billion kilometres into the units this video is built on, and you get a number that does something unpleasant to the chest. 0.0027 light-years. Not 2.7, not 0.27, 0.0027 light-years out of 100,000. Go back to the grains of sand for a moment, because this is where that model earns its keep. 2 grains, 29 kilometres apart, and that is the shortest gap in the entire galaxy. In 49 years of unbroken flight, our fastest departing machine has covered, at that scale, about 18 metres, 18 metres of 29 kilometres to the very nearest grain. And now, the arithmetic for the crossing. At 17 kilometres per second, 100,000 light-years takes approximately 1.76 billion years. I want to put a floor under that number, because billion has become a word people hear without flinching. 1.76 billion years ago, on Earth, there were no animals. There were no plants. There was nothing multicellular of any consequence anywhere on the planet. Life consisted of single cells in water, and the atmosphere had only comparatively recently acquired free oxygen, which had been an ecological catastrophe for most of what was living at the time. Multicellular life would not appear for well over 1 billion more years. The continents were arranged in configurations that have no modern names. If Voyager 1 had been launched then, aimed across the galaxy, and had never encountered anything, and nothing had ever slowed it, it would be arriving at the far rim right about now. That is our machine, that is the best we have, and let me preempt the obvious objection, because there is a faster object and it is worth doing properly. The Parker Solar Probe holds the record for the fastest speed ever achieved by anything humans have built. On the 24th of December, 2024, following a gravity assist at Venus that tightened its orbit, it swept through its closest approach to the Sun at 192.2 kilometers per second. That is 692,000 kilometers per hour, 430,000 miles per hour. It is a formally recognized world record, and it is a genuinely astonishing engineering achievement. It is also 0.064% of the speed of light. At that speed, crossing 100,000 light-years takes about 156 million years, and that figure is far too generous, because Parker's record speed is not a cruising speed. It is a falling speed. The probe reaches 192 kilometers per second at the very bottom of a plunge into the Sun's gravity well, in the same way a skydiver reaches terminal velocity, by falling, not by pushing. It cannot hold that speed. As it climbs back out, it slows down again. There is no version of the Parker Solar Probe that leaves the solar system at 430,000 miles per hour, because the Sun that granted it the speed also takes it back. So the honest comparison is not 156 million years. It is somewhere considerably worse, and the only object we have that genuinely maintains its departure speed is Voyager, at 17 kilometers per second, giving 1.76 billion years. There is a nearer comparison that makes the point even more sharply than the galaxy does. Proxima Centauri, the nearest star to the Sun, is 4.24 light-years away. At Voyager's 17 kilometers per second, reaching it would take about 75,000 years, not to cross the galaxy, to reach the single closest star, the first grain of sand at 29 kilometers, 75,000 years, which is roughly the span between the last major glacial period and now, and considerably longer than any human institution has ever survived. And Voyager is not going there, which is worth saying because it is often assumed to be. It is not aimed at anything. None of our departing spacecraft are. They were aimed at planets, and their present trajectories are whatever the planets left them with. It is also worth being clear about why we cannot simply build something faster, because this is not a failure of ambition. The problem is that a rocket has to carry its own fuel, and the fuel has mass, and the mass has to be accelerated too. Wanting more speed means carrying more fuel, which means more mass, which means needing more fuel to move it. The relationship is not proportional, it is exponential. Every increment of additional velocity costs enormously more than the one before it. This is why the enormous rockets we launch deliver such small payloads, and why gravity assists, stealing a little orbital momentum from a passing planet, have been the workhorse trick of interplanetary flight for 50 years. We do not accelerate our probes to these speeds, we arrange for planets to throw them. New Horizons, the probe that flew past Pluto in 2015, and is now the third fastest departing object, is leaving at about 16.3 kilometers per second, slightly slower than Voyager, launched nearly 30 years later, with the benefit of 3 decades of progress. That is the state of the art. It has not moved. Let me stay with Voyager for a moment, because there is something about where it is now that I think about more often than is probably healthy. It is dark out there. Not dim. Dark. The Sun, from Voyager's position, is no longer a disk. It is a point. It is the brightest star in that sky by a wide margin, but it is a star, and it casts no useful light and provides no warmth. That is why the probe runs on plutonium instead of solar panels. Inside, the plutonium is decaying, exactly as physics said it would in 1977. Every year there is a little less power. Over the past decade, instruments have been shut down one by one to keep the essential systems alive. Heaters switched off, experiments retired, the machine narrowing itself down to keep talking. Sometime in the next several years, the power will fall below what any instrument needs, and the transmissions will stop. Voyager will not end at that point. It will simply go quiet. It will keep travelling at 17 kilometers per second, in the same direction, for as long as nothing interferes with it, which is likely to be a very long time indeed. Its plutonium will finish decaying. Its aluminium will slowly erode under cosmic rays. The gold-plated record bolted to its side, with its greetings in 55 languages and its recordings of birdsong and thunder and a Bulgarian folk song will go on being unplayed. And in 1.76 billion years, having covered 100,000 light-years, having crossed the entire galaxy, it would arrive at the far rim, long after the sun has swollen and changed and burned Earth's oceans away, long after there is anyone anywhere to notice, carrying a set of instructions on how to build a record player, addressed to nobody. It is not aimed across the galaxy, incidentally. It is heading up and out of the plane of the disk toward the constellation Ophiuchus. In about 40,000 years it will pass within about 1.6 light-years of a small red dwarf called Gliese 445. That is the closest it will come to anything for a very long time, and 1.6 light-years is not close. It is a wide miss in an empty room. So this is the second answer, and it is the answer that ends the conversation for anything humans currently know how to build. How long would it take to cross the Milky Way? Roughly 1.76 billion years, using our best actual machine. Perhaps 156 million using the highest speed we have ever momentarily touched, if we could somehow hold it, which we cannot. Even the optimistic proposals do not rescue this. A fusion drive running at the theoretical limits people quote, 10% of light speed, crosses the galaxy in 1 million years, still more than 3 times longer than our species has existed. The most aggressive concept anyone takes seriously, a gram-scale sail pushed to 20% of light speed by a ground-based laser array, would take 500,000 years, and could not slow down at the far end even if it survived the trip. And here is the detail that ought to sting most. The sun is faster than all of it. 230 kilometers per second, permanently, with no engine, for 4.5 billion years. If the sun travelled in a straight line rather than a circle, it would cross the galaxy in about 130 million years, beating every machine we have ever launched by a factor of more than 10. We have not built anything that outruns the rock we are standing on, and the rock is going in circles. So we now have 2 answers. 100,000 years for light, which nothing can beat. 1.76 billion for us, which is a polite way of saying never. Both of those answers are correct. Both of them are also answers to a question about a straight line drawn across a distance of 100,000 light-years, which is when it becomes reasonable to start asking a much more awkward question. We have been assuming that number. Everyone quotes that number. It is on every diagram and in every textbook. Where does 100,000 light-years actually come from? And is it the width of anything at all? Imagine standing in a room where the walls do not exist, and the floor simply gets fainter the further out you walk, and at some point somebody has painted a line and written the word outside on the far side of it. That is the situation with the diameter of our galaxy, and once you see it, you cannot unsee it. Every number I have used so far in this video rests on one figure, 100,000 light-years. It is on every diagram. It is in every textbook. It is the number you would give if somebody stopped you in the street and asked how big the Milky Way is. It is not a measurement of an edge. There is no edge. It is a threshold that astronomers agreed on, and it was chosen for perfectly sensible reasons, and it is a convention. Here is what actually happens as you travel outward through the disk. The density of stars declines. Then it declines further. It does not stop. There is no radius at which the last star sits with nothing beyond it. The disk fades, and it flares as it fades. Remember, it gets vertically thicker toward the rim while getting sparser, and it merges gradually into the halo, which itself thins out over hundreds of thousands of light-years with no boundary of any kind. To produce a diameter from that, you have to pick a level of surface brightness, or a level of star density, and declare that below it you are no longer in the galaxy. Different reasonable choices give different diameters. That is not a scandal. It is simply what measuring a diffuse object means, and the choices genuinely disagree. In 2018, a group working with spectroscopic data from the Sloan Digital Sky Survey and from Epigee approached the problem chemically rather than by brightness. Stars that belong to the disk population have a characteristic chemical fingerprint, particular ratios of iron and other elements, which distinguishes them from halo stars. So instead of asking where the light gets too faint, they asked how far out you can still find stars with disk chemistry. The answer was considerably further than 100,000 light-years. Their work supported a disk extending to something in the region of 200,000 light-years across, and it generated a wave of headlines pointing out the obvious consequence. that crossing our galaxy at the speed of light might take not 100,000 years but 200,000. The crossing time had just doubled, and nothing about the galaxy had changed. Only the definition had, and the hydrogen goes further still. Neutral hydrogen gas, mapped at 21 centimetres, has historically been traced out beyond 150,000 light-years in diameter, further than the classical stellar disk, thinning gradually, warping as it goes. So already we have 3 defensible answers to a question that sounds like it should have one. 100,000, 150,000, 200,000. Each is correct for its own definition. None of them is the edge, because none of them is an edge. It is worth saying that this is not a peculiarity of our galaxy, or a consequence of our awkward viewpoint inside it. Every galaxy has this problem. When you read that a galaxy is a certain number of light-years across, you are reading a number produced by choosing a brightness contour and measuring to it. Astronomers are entirely open about this. The conventions have names and the papers state which one was used. The tidiness is in the reporting, not in the universe, and our own galaxy's quoted size has been spectacularly unstable within living scientific memory. Herschel's map in the 1780s implied a system a few thousand light-years across. Kaptein's model in 1922 gave about 40,000. Shapley's globular clusters, uncorrected for dust, gave something like 300,000. The modern 100,000 emerged only once the dust was properly accounted for, and now the chemical surveys are pushing it back up again. The number has moved by more than an order of magnitude in 100 years, and none of those revisions happened because the galaxy changed. They happened because the definition sharpened, or the correction improved, or somebody thought of a better question to ask. Now let me show you what happens when you stop asking where the light stops and start asking a different question entirely. In 2020, a group of astronomers led by Alice Deason and Azadeh Fattahi took a genuinely different approach to the boundary problem. Rather than looking for where stars run out, they looked for where the galaxy's gravitational authority runs out, specifically for the surface at which material that has been falling inward toward the Milky Way for billions of years finally turns around. Inside that surface, matter belongs to us. Outside it, matter is still on its way in, or not coming at all. That is a physical boundary rather than a brightness threshold. It is the edge of what the galaxy owns. They found it at a radius of roughly 950,000 light-years, which gives our galaxy a diameter of approximately 1.9 million light-years, give or take about 0.4 million, 19 times the number in the textbooks. Take a moment with that, because it is the point in this video where the ground properly moves. You have spent an hour building a picture around 100,000 light-years. You have watched me calculate crossing times against it, and the object we live in, defined by where its gravity actually holds sway, is 19 disk widths across, and the bright spiral we have been discussing sits in the middle of it like a coin in a stadium. There is no moment at which you would leave the Milky Way. That is what this really means. If you set off outward tonight in a straight line at any speed you like, there is no boundary you would cross, no threshold you would feel, no last star, no gate. The stars would thin. Then they would thin more. At some point, hundreds of thousands of light-years out, you would be surrounded by a scattering of ancient halo stars and globular clusters, and essentially nothing else. And the disk behind you would look like a distant lit object rather than a place you were in. And you would still be inside the galaxy, by the only definition that describes a real physical thing. You would never leave. You would only at some point a very long way out notice that you had. And this is not a semantic dodge or a piece of philosophical throat clearing. It has real consequences for real questions. If you want to know whether a passing dwarf galaxy is a satellite of ours or an independent object drifting nearby, you need a boundary. If you want to know how much mass the Milky Way contains, you need to know what counts as inside. If you want to know whether we and Andromeda have already begun to interact, you need to know how far each of us reaches. The edge is not decorative, it is load-bearing, and it is a decision. We do not have an intuition for objects like that. Everything we handle has a surface. A rock stops. A body of water stops. Even a cloud, which is the closest everyday analogue, has an outside where you can stand and look at it. A galaxy has no outside anywhere near it. It has a bright middle and an enormous diffuse claim. Now, the numbers this does to the crossing question are almost comic. At the speed of light, crossing the full gravitational extent of our galaxy, 1.9 million light-years, takes 1.9 million years. Not the 100,000 we have been working with. 19 times that. Light itself, which cannot be beaten by anything, would need almost 2 million years to get from one side of this object to the other. For Voyager, at 17 kilometers per second, the same crossing runs to something around 33 billion years. The universe is 13.8 billion years old. Our fastest departing machine would need more than twice the entire age of the universe to cross the object we live in, if we are honest about how wide that object is. And there is a beautiful, slightly unnerving consequence sitting next to this that puts a scale on the whole neighbourhood. Andromeda, the nearest large galaxy, is 2.5 million light-years away. Our halo reaches roughly 950,000 light-years out. Andromeda is a comparably sized galaxy with a comparably sized halo. Add those together, and you get something close to 2 million light-years of combined reach across a gap of 2.5 million. The two galaxies are nearly touching already. Whatever the merger 4 or 5 billion years from now is going to be, it has arguably started. There are other things out there in the space we have just enlarged, and they help make it feel less abstract. The Large Magellanic Cloud, a substantial satellite galaxy visible to the naked eye from the southern hemisphere, sits about 160,000 light-years away. The Small Magellanic Cloud is at roughly 200,000. Both of them lie well outside the classical stellar disk, and both are well inside the halo. They are not neighbours of the Milky Way, they are contents of it. Around 60 satellite galaxies are known in total, most of them faint dwarf systems, and one of them is currently being destroyed in front of us. The Sagittarius dwarf galaxy is being pulled apart by our gravity, and the stars stripped from it have been drawn out into a stream that wraps entirely around the Milky Way, a loop of stolen stars larger than the whole stellar disk. Our galaxy is eating, slowly, and the meal is visible in the data. So the question we started with has quietly changed shape again. When you ask how long it takes to cross the Milky Way, you now have to specify not only whose clock you are reading, but which Milky Way you mean. The bright spiral, the extended chemical disk, the hydrogen, the gravitational domain. And there is one more revision to come, and it is the largest of them all. Because everything I have described so far, the stars, the gas, the dust, the entire luminous structure this video has been built around, is a minority component of the galaxy by mass. The overwhelming majority of what makes up the object we live in has never emitted a single photon, has never been directly detected, and is passing through your body right now. Watch a set of planets go round a star, and they betray where the mass is. Mercury, close into the Sun, moves at about 47 kilometers per second. Earth, further out, moves at about 30. Neptune, right out at the edge of the planetary system, crawls at about 5.5. The pattern is clean, and it is exactly what Newton predicts when nearly all the mass of a system is concentrated in the middle. The further out you go, the slower things orbit, because there is less gravity out there pulling you round. Every solar system does this. Every set of moons does this. It is one of the most reliable relationships in physics. Now do the same measurement on our galaxy. If almost all the mass of the Milky Way were in its stars, and its stars are heavily concentrated toward the middle, then stars in the outer disk should orbit far more slowly than stars near the centre, in exactly the way Neptune lags behind Mercury. They do not. The orbital speed rises steeply in the inner galaxy, and then simply flattens out and stays flat, all the way to the limits of what anyone can measure. Stars 50,000 light-years from the centre are going round at broadly the same speed as stars half that distance out. The curve does not fall. It refuses to fall. This was not an easy result to establish, and it was not immediately believed. The measurements that made it undeniable were made in the 1970s by the American astronomer Vera Rubin, working with the instrument builder Kent Ford. They took spectra of the outer regions of Andromeda, and then of dozens of other spiral galaxies, measuring how fast the gas at each radius was moving. Galaxy after galaxy gave the same result. The curve went up and then went flat and stayed flat, out past the point where the visible light had faded away to nothing. Rubin was careful about how she presented it. She did not claim to have discovered an invisible substance. She reported what the rotation curves did, over and over, in system after system, until the pattern became impossible to attribute to error. The interpretation arrived afterwards, and the modern field of dark matter research grew out of a body of unglamorous patient spectroscopy that most of the discipline initially found uninteresting. There are only two ways to read that, and both of them are uncomfortable. Either there is a great deal more mass out there than we can see, arranged so that it keeps contributing gravity as you move outward, or gravity itself does not behave the way we think it does when the pull gets very weak. The mainstream reading is the first one, and it has a name you have heard, dark matter, and when the numbers are worked through, they are not marginal. The most widely cited modern determination came in 2019, from a combination of the Hubble Space Telescope and Gaia. The method is elegant. Take globular clusters, those ancient swarms of stars scattered around the halo, and measure how fast they are moving. They are test particles falling in the galaxy's gravity, and their speeds tell you how deep the gravitational well is. Gaia tracked 34 of them out to around 65,000 light-years. Hubble, looking further, tracked another dozen out to about 130,000. 46 clusters, three-dimensional motions, one answer. The Milky Way contains approximately 1.5 trillion times the mass of the Sun, within a radius of 129,000 light-years, 1.5 trillion solar masses. Now compare that with what is lit. The total mass of all the stars in this galaxy, every one of the 100 to 400 billion of them, including the Sun, comes to something like 60 billion solar masses. The gas and dust between them adds perhaps another 10 billion. 60 billion against 1.5 trillion. The stars are about 4% of our galaxy. Everything luminous, everything that has ever emitted light, everything this video has spent an hour and a half describing, is a 4% contaminant in something else. Go back to the very first image in this video, the band of pale light arching over a dark field. I called it a wall of stars seen edge-on, and that was true, and it was the whole picture at the time. Here is the same image with everything we now know loaded into it. That band is a thin, bright smear of ordinary matter, 100 times wider than it is deep, sitting near the middle of a roughly spherical cloud nearly 2 million light-years across, made of something that gives off no light, absorbs no light, reflects no light, and outweighs the smear by a factor of 25. The Milky Way is not a spiral of stars. The Milky Way is a dark sphere with a spiral of stars in it. If an observer had no access to visible light at all, and could detect only mass, and were asked to describe our galaxy, they would describe the halo. They would talk about a roughly spherical distribution about 1.9 million light-years across, denser toward the middle, with a small flat luminous impurity near the centre that a careful survey might or might not bother to mention. That description is more accurate than the pinwheel on the poster. It is also, as far as anyone can tell, the reason there is a galaxy here at all. Without a dark halo, the ordinary matter would never have collected into a disk this size in the time available. The structures we see in the early universe formed around dark matter first, with gas falling into wells that were already there, and without it now, the galaxy would not hold. A disk rotating this fast with only 60 billion solar masses to bind it would have shed its outer regions long ago. The stars stay in their orbits, because something we cannot see is holding them, and the material is not somewhere else. This is the part people find hardest. The dark matter halo is not out at the rim, it is densest toward the centre, and it passes right through the disk. The local density is estimated at around 3 to 4 tenths of a giga-electronvolt per cubic centimetre, which in more ordinary terms is roughly the mass of one hydrogen atom in every 3 cubic centimetres of the room you're in. It is going through you as you listen to this. It has been going through you your whole life. It goes through the Earth as though the Earth were not there, because it does not interact with ordinary matter except by gravity, and gravity at that mass scale is far too feeble to notice. We have been trying to catch it for decades. Enormous detectors, buried under kilometres of rock to screen out everything else, filled with tons of liquid xenon cooled to well below freezing, waiting for a single dark matter particle to happen, to clip a single atomic nucleus hard enough to produce a flash. Experiments called Xenon, LZ, Pandex and others have run for years, improving their sensitivity again and again. They have not found it. Every campaign has pushed the exclusion limits further without a confirmed detection. That is not proof it is not there. The rotation curves are still flat. The gravitational lensing of distant galaxies still requires unseen mass. The structure of the early universe still demands it. But it is a real and honest tension, and it is the reason a minority of serious researchers keep working on the other answer. Which brings us to the alternative, and it deserves to be stated properly rather than dismissed. In 1983, an Israeli physicist named Mordechai Milgram proposed that instead of adding invisible mass, we should modify the law of gravity. His idea, called modified Newtonian dynamics, or MOND, is that below a certain very small acceleration, around 1.2 times 10 to the minus 10 meters per second squared, which is a fantastically gentle tug, gravitational attraction stops falling off as the square of distance and falls off more slowly instead. Do that, and the flat rotation curves come out automatically, with no dark matter required. MOND is not fringe nonsense. It is a real proposal in the physics literature, and at the scale of individual galaxies it works remarkably well, often predicting rotation curves more accurately than dark matter models do, using nothing but the visible matter and one universal constant. The tightness of the relationship between a galaxy's ordinary mass and its rotation speed is a genuine empirical result that any complete theory has to account for. Where MOND runs into difficulty is everywhere larger. It struggles to explain the mass distribution in clusters of galaxies without reintroducing some unseen matter anyway. It does not naturally reproduce the detailed pattern of the cosmic microwave background. And there is one particular observation that is very hard for it. The Bullet Cluster, a collision between two clusters of galaxies observed in 2006, in which the gravitational mass measured by lensing is clearly separated in space from the hot gas that contains most of the ordinary matter. The mass went one way, the visible material went another. That is close to exactly what you would expect if most of the mass were a collisionless substance that passed through the collision untouched, and it is very awkward if the mass is simply the visible matter obeying a modified rule. A relativistic version of MMOND was constructed, and it was substantially constrained in 2017 when the neutron star merger designated GW 170817 showed that gravitational waves and light travel at the same speed, ruling out a class of models that required them not to. So the fair summary is this. MOND fits galaxies beautifully and the universe badly. Dark matter fits the universe beautifully and individual galaxies with more effort. Most working astrophysicists take the second position, a minority takes the first, and the honest thing to say is that we are describing the dominant component of the object we live in without knowing what it is. We know how much of it there is. We know roughly how it is arranged. We know it is passing through your body at this moment. We do not know what it is made of, and no experiment has ever held any. And with that, the picture of the thing we are trying to cross is finally complete. A small bright sheet inside an enormous invisible sphere, both of them fading outward with no edge, all of it in motion, none of it going anywhere. So it is time to answer the question properly, and the real answer does not involve going faster. Picture a ship with a flaw. Not a spinning wheel, not a centrifuge, nothing clever. A ship with an engine at the back that never switches off, pushing forward hard enough that everything inside is pressed toward the rear wall with exactly the force you feel right now sitting on the Earth. One gravity, ordinary weight. You could put a glass of water on a table and it would sit there, perfectly still, for years. That is the entire design. There is no exotic physics in it. Nothing here breaks a rule, bends a rule, or requires a wormhole, a warp field, or a shortcut of any kind. It is a ship that accelerates gently, and keeps accelerating and never stops, and it crosses the Milky Way in about 22 years. I want to be very careful with that sentence, because it is the payoff of this entire video, and it is extremely easy to hear it wrong. The ship does not go faster than light. Nothing does. Nothing can. From outside, watching, the crossing takes a little over 100,000 years, exactly as I told you in part 7, and not 1 second less. The flaw I gave you earlier still holds and it will always hold, but the 22 years is also true. It is the time that passes on the ship. It is the number of birthdays the crew has. It is how much they age. Here is how both of those can be correct at once. At everyday speeds, time and distance behave the way your intuition says they do, because your intuition was assembled at walking pace. As you approach the speed of light, two things happen, and they are not illusions or measurement errors. They are what space and time actually do. The first is time dilation. A clock moving very fast relative to you runs slow, as measured by you. The faster it goes, the slower it runs, and there is no limit to how slow it can get. The second is length contraction, and it is the one that actually does the work here. From the point of view of something moving very fast, distances in the direction of travel are shorter. Not apparently shorter. Shorter. The universe ahead of a fast traveller is compressed along their line of motion, and the closer to light speed they get, the more it flattens. So the crew of that ship do not cross 100,000 light-years quickly. They cross a much smaller galaxy at a perfectly reasonable pace. Now the numbers, because they are extraordinary, accelerate at 1 gravity, and after about a year of ship time, you're already travelling at roughly 3/4 of the speed of light. After a few more years, you're at 99.9%, then 99.99, with more nines arriving steadily. You never reach light speed, and you never need to. For 100,000 light-year crossing, you accelerate for the first half, then turn the ship around at the midpoint and decelerate for the second half, so that you can actually stop when you arrive rather than passing through at unimaginable speed. Work that through with the relativistic rocket equations, and the proper time, the time on the ship's clock, the time on the crew's bodies, comes to approximately 22 to 23 years. At the midpoint, the moment of the flip, the ship's Lorentz factor exceeds 50,000. That is the number that governs everything, and it means that at that instant 1 second aboard corresponds to something like 14 hours in the galaxy outside. Sit down for lunch, and while you eat it, several years pass on the world you left. And the galaxy in front of the ship at that moment is not 100,000 light-years across. Divide by that Lorentz factor, and it is under 2 light-years wide. The entire disk, the arms, the bar, the 100 billion stars, the whole structure this video has spent 2 hours describing, has flattened in the ship's frame to something narrower than the gap between the Sun and Proxima Centauri. The crew are not crossing a large galaxy fast. They are crossing a small galaxy at a normal speed. That is the actual mechanism, and it is the single most beautiful thing in this story. Run the same calculation for Andromeda, 2.5 million light-years away, and it comes to about 28 years of ship time. That figure has been in the physics literature for decades, and it is a useful check on the first one because notice what it says. Increasing the distance by a factor of 25 adds only 6 years to the traveller's life. Under constant acceleration, distance stops mattering almost entirely. The observable universe itself is a matter of decades. So let me sit you inside it for a moment. You are aboard. The floor is under your feet and it feels like Tuesday. There is no sensation of motion at all. There never is under smooth acceleration, which is the whole point of Einstein's insight, and it is the same reason you cannot feel the Earth going round the Sun. Nothing rattles. A pen left on a table stays where it is. Outside, the view has become something no human eye has been designed for. The stars ahead have crowded forward into a compressed ring of hard blue light, dragged in from behind by the geometry of your own speed, while astern the sky has emptied and reddened into darkness. There is no star field anymore. There is a bright ring in front and nothing behind. There are 2 clocks that matter. The one on the wall ticking exactly as it always has, because clocks always tick normally for the person standing next to them, and the other one, the one you have to work out on paper, running 14 hours for every second of yours. Halfway, the ship turns. The engine keeps burning and the floor stays where it is. Only the direction of travel changes relative to the thrust. Nobody feels a thing. 22 years pass. People age. Somebody's children grow up on board. Then you arrive, and you step out onto the far rim of the galaxy, and the crossing is complete, and you are 22 years older. And everyone you left is 100,000 years gone. Not dead. Gone, in the way that species and languages and continents worth of history are gone. The Earth you departed from is separated from you by a stretch of time 3 times longer than anatomically modern humans have existed. Whatever is there now, if anything is, has no more connection to what you left than you have to the people who painted the caves at Lascaux, and considerably less. That is the third answer. That is the real one. How long does it take to cross the Milky Way? 22 years and 100,000 years, and both numbers describe the same journey. There is no contradiction to resolve. There is simply no such thing as the duration of a journey. There is only duration measured by a specified clock, and the 2 clocks in this story disagree by a factor of about 4,500, and physics is entirely comfortable with that. Now let me take it away from you, because I promised honesty, and this is where honesty costs something. We cannot build it. Not yet. Not with any technology anybody has drawn a credible diagram of. The energy is the killer. Pushing a ship to the Lorentz factors involved requires converting a mass of fuel into energy, with essentially perfect efficiency. And even a flawless antimatter rocket faces a fuel requirement that grows exponentially with the speed you want. The masses come out absurd. You very quickly need more fuel than the galaxy contains to move a payload the size of a house. Every proposal that avoids carrying fuel runs into a different wall. The interstellar ramjet, proposed in 1960, was supposed to scoop hydrogen from space as it went. Later analysis suggested the drag from the scoop would exceed the thrust it could generate, which turns the engine into a brake. And even with infinite fuel, there is the medium. I told you earlier that interstellar space contains about 1 atom per cubic centimetre, and that this is a better vacuum than we can manufacture. At a Lorentz factor of 1,000, those atoms are not a vacuum. They are a beam. Each one arrives at the hull with the energy of a particle from an accelerator, and the ship is flying into a continuous, unavoidable flood of them. Nobody has a shield for that. So the 22 years is real physics and not an engineering plan. It is a statement about what the universe permits, not about what we can do. There is an alternative, and it is the one that most serious proposals fall back on, and it is worse in a quieter way. If you cannot go fast, go slow and outlive the journey. Build something enormous, put people inside it, accelerate it to a few % of light speed by any means available, and let the crossing take 1,000,000 years while generations are born and die aboard. No relativity required, no absurd energies, just patience, on a scale nothing human has ever demonstrated. The difficulty there is not engineering either. It is that no institution, no language, no belief system, and no genome has ever remained recognizably continuous across 1,000,000 years. Nothing we have built has survived even 1% of that. The ship would arrive, and whatever was aboard it would have no meaningful relationship to whoever launched it, and the mission it was sent on would be, at best, a rumor. And there is one route that solves the problem completely, which is to stop sending people. A self-replicating machine, a probe that arrives somewhere, builds copies of itself out of local material, and sends those onward, does not care about a 1,000,000-year journey. Run that arithmetic, and even at modest sublight speeds, a single such probe could reach every star in the galaxy within a few million to a few tens of millions of years. Against 13 billion years of galactic history, that is essentially instantaneous, which means the galaxy is crossable, comprehensively, by something patient and mindless, and always has been. Go back one last time to the grain of sand and the 29 kilometres. In Part 4, that gap was a picture of emptiness. In Part 8, it became a measure of failure, 18 metres covered in 49 years. And here it inverts one final time, because the emptiness that made the journey impossible is exactly what makes it survivable. A ship at these speeds could not tolerate a crowded galaxy. It is only because there is nothing between the grains that a relativistic crossing is even conceivable. The same vacuum that makes the trip pointless is the only reason it could ever be made. But notice what it has done to the question. We started this video asking how long it takes to cross our galaxy, as though that were a property of the galaxy, like its mass or its width, something you could look up, and it is not. The crossing time is not a fact about the Milky Way at all. It is a fact about the relationship between the galaxy and whoever is doing the crossing, which means the answer to the question in the title has been, this whole time, for whom? And there is one more consequence hiding in all of this, and it is the one that has kept people awake for 60 years. If the galaxy can be crossed within a single lifetime, even in principle, even with absurd energy, then the galaxy has been crossable for a very long time, and it looks empty. 13.6 billion years ago, before the Earth, before the Sun, before almost anything you could put a name to, this galaxy began pulling itself together out of gas. It has been turning ever since. Light has crossed it, one rim to the other, something like 130,000 times over. There has been more than enough time for anything patient to go anywhere in it, many times, in every direction, and when we look, we find nothing moving through it but light. I want to be careful about how I hand that to you, because it is not a horror story, and I am not going to pretend it is one. It is simply the last thing that falls out of the arithmetic, and it falls out cleanly. We spent this video establishing that the galaxy is enormous, and it is. But every single time we found a reason it should be uncrossable, the reason failed. The distance is not the obstacle. The Sun eats a full galactic diameter every lap and has done so 20 times. The emptiness is not the obstacle. There is nothing in the way, and the vacuum is the only reason a fast crossing is even conceivable. And the time is not the obstacle either, not in principle, because the time depends entirely on whose clock you read, and a traveller willing to keep accelerating crosses the whole thing in 22 years. The galaxy is not too big to cross. That was the assumption we started with, and it did not survive, which leaves the silence needing a different explanation, and I do not have one for you. Nobody does. That is not a failure of this video. It is the actual state of the question. The most honest thing I can say is that whatever answers it, it is not the size, because we have just spent 2 hours watching the size fail to be an obstacle. There is a way of holding the timescale that helps, and it is worth doing slowly. Compress the entire life of this galaxy into a single calendar year. The gas begins collapsing in the first seconds of the 1st of January. The oldest globular clusters, the ones Shapley used to find the centre, form within the first day or two. The disk settles over the following weeks. The Gaia Sausage Enceladus collision, the one that may have bent the disk we still live in, happens somewhere in the spring. The Sun does not form until the beginning of September. The Earth cools and acquires oceans within days of that. Life appears more or less immediately afterwards, and then does very little for months. Multicellular organisms arrive in mid-December. The dinosaurs occupy the last week and are gone by the 29th or 30th. Anatomically, modern humans appear about 11 minutes before midnight on the 31st of December. All of recorded history, or every civilization, every written word, every name anybody remembers, occupies the last 0.2 of 1 second. And in that same year, light crossed this galaxy 130,000 times. 360 crossings while human civilization happened. Roughly 1 complete crossing of the Milky Way, rim to rim, for every day of the galaxy's life. That is the ratio that does it for me, more than any of the raw figures. The crossing that would consume everything we are is, on the galaxy's own accounting, a daily event. And the disk has an expiry date, which is worth saying plainly because it is easy to think of these structures as permanent. In roughly 4 to 5 billion years, Andromeda arrives. The two galaxies will pass through each other, and their disks will not survive the encounter. The arms will be pulled out into streams. The gas will be compressed and burn itself out in a final burst of star formation. What is left afterwards, some billions of years later, will be a single large elliptical system with no disk, no spiral pattern, and no band of light in anybody's sky. Everything I have described tonight is a phase, a long one, and one that happens to overlap with us, and one that will end. So let me finish somewhere quieter and closer to home. Go back to where we started. A field somewhere far from any town. No moon. Your eyes have adjusted, and a band of pale light is arching over you from one horizon to the other. At the beginning of this, I told you that band is not an object in the sky, that it is a wall of stars you're looking at edge on from the inside. That was true, and it was as much as the picture could hold at the time. Look at it now with everything loaded in. That band is a sheet of stars 100,000 light-years wide and 1,000 thick, 100 times wider than it is deep, closer in proportion to a sheet of paper than to anything with thickness. It is bent by something we have not identified. It thickens toward a rim that is not a rim because it fades rather than ending. It has an unresolved number of arms which are not structures but congestion. It is almost entirely empty, grains of sand 29 kilometers apart, in a volume where 2 galaxies could pass straight through each other without a single collision. The brightest part of it, low in the south in summer, marks a centre 26,673 light-years away, holding 4.3 million solar masses in a space smaller than the orbit of Mercury, which no human eye has ever received a photon from and never will. And the whole of that bright sheet, every star in it, every nebula, all of it, is about 4% of the mass of the object it sits in. The rest is a dark sphere nearly 2 million light-years across, which we cannot see, cannot catch, and cannot identify, and which is passing through your body while you stand in that field. That is the true scale of our galaxy, not the number, the relationship between the part you can see and the part you cannot. And the thing I keep coming back to, the thing that stays with me longer than any of the numbers, is the shape of the answer we ended up with. The Milky Way can be crossed inside a single human life. Physics permits it outright, not with a shortcut, not with a loophole, not with anything that violates a rule, just with an engine that does not stop and a willingness to keep going. 22 years, and a person steps out at the far rim of the galaxy, having aged less than the time it takes to raise a child. And the price of that ticket is everything they were leaving from. 100,000 years pass at home, while 22 pass on the ship. Arrival and loss are not two separate outcomes of the journey. They are the same event, and there is no version of the trip where they come apart, because the very thing that makes the crossing short is the thing that makes the return impossible. The galaxy is not too big to cross. It is exactly big enough that crossing it is indistinguishable from never coming back. I do not think that is a sad fact, though I understand why it lands that way at first. I think it is one of the strangest and most specific pieces of information a person can hold, that we live inside something crossable, and that nothing has visibly crossed it, and that the reason has nothing to do with how far anything is. It is also worth saying that none of this makes the ordinary sky less worth looking at. If anything, it goes the other way. The stars you can actually see are the nearest 100 or so systems out of 200 billion, and that turns out to be the point rather than the disappointment, because those few thousand points of light are the only part of this entire structure that any human being has ever perceived directly, with their own equipment, without an instrument in between. Every other fact in this video arrived through a telescope, a radio dish, a detector, or a calculation. The band is the one part you get to receive yourself. There is one more thing, and then I will leave you to sleep. Every number in this video is provisional. I have tried to be honest about that throughout, because I think it is the most interesting part. The diameter is a threshold somebody chose, and it has moved by more than a factor of 10 within 100 years. The number of arms is unsettled. The warp is real, and nobody knows what is bending it. The precession rate disagrees with itself by a factor of 2 depending on which stars you ask. 95% of the mass is unidentified. We have individually catalogued about one star in 100, after the finest survey ever flown spent more than a decade doing nothing else. We are, in other words, quite early. The map is good and it is not finished, and the people making it have always known they would never see the thing they were drawing. So the next time you're somewhere dark enough and that band comes out of the sky, you will know what you're looking at. Not a river, not spilled milk, not a feature. A wall of 100 billion suns, seen edge-on from a seat about halfway out, with almost 2 million light-years of something we cannot see wrapped around all of it. And it is not above you, whatever the sky suggests. There is no above. You're in the middle layer of it, held in place by the same gravity that holds everything else, moving at 230 kilometers a second in a direction nobody ever points out, on a lap that will not finish for another 200 million years. The band is not overhead. The band is the room, and you have never once been outside it, and neither has anyone. And you will know the answer to the question we started with, which is that there isn't one. There is only ever the question of whose clock you are reading. Sleep well.